What do skydiver, a cup of coffee, and charging your phone battery have in common? Surprisingly, they can all be described using the same kind of mathematics: differential equations. These equations model how systems change over time, and once you understand them, you will start seeing math everywhere. This is both a promise and a threat. So welcome to lecture 31, the differential equations describing real-world scenarios. Today we will cover a few of the differential equations that actually describe the systems we witness in our everyday lives, and of course, this has some overlap with previous and future lectures, but that just means you will learn it better. So our first example would be a hot cup of coffee. Just like with any system and differential equation, we must first try to describe its behavior. We know that its temperature will be highest at the start, so we can say it's hot. And then we know that it will cool down faster at the start, but will take longer to reach room temperature. Why? Well, there is a lot of factors. The heat must pass on to the air around the cup. That air has to make way for fresh air to come closer or give its heat away to the outer air layers. And when we get to thermodynamics, we will see that greater heat difference makes heat dissipate faster. So we could write it like this. All in all, we could say that the cooling depends on this single factor right here, or mainly on this factor right here. The difference between the temperature of the coffee, marked with T, and the temperature of the room, T room. The unit here is kelvins, because temperature, although since it's the difference, it could work with Celsius too. However, that does depend on other units and constants that we are given. But anyway, let's build our differential equation. So we said that change of temperature over the change of time is proportional to the difference in temperature. However, difference in temperature refers to the change in variables. So in this case, well, yeah, technically there is two ways I could explain this. First is that delta T is the difference between any two temperatures, regardless of their relationship, so whether the initial or final one is the first one, and the initial or final, the other one, is the second one. So the relationship doesn't matter, but it's the sign in front of the delta, so we could have a plus or minus delta, and that sign in front of it would refer to the direction. So in this case, minus could be for reduction of overall temperature, or plus for increment. Or second, that delta T would simply refer to the final temperature minus the initial temperature, which for our cup of coffee is the temperature of the room minus the temperature of the coffee at the start. Since the room temperature is lower than that of the coffee, we can change the order and carry a minus in the front. So this temperature of the room, let's say it's 25 degrees Celsius, and temperature of the coffee would be 40. So if we want inside the bracket to be positive, because this is a greater number that's subtracted from the lower one, the result would be negative. So I can switch these two around and carry a minus in front. That is why it's important to know systems. In physics, especially after vectors, the minus sign will know the direction we're taking. However, we can choose which direction that will be. We could define heating as positive, as we can see here, and that would make cooling negative. Or we could turn it around and say that cooling is set as positive, that makes heating negative. As long as you're consistent with what you're doing, your result can be correct. Well, of course, as long as you do not mess up your calculations. But yeah, it's important to imagine the system and try to explain it, and then set a reference point. If we have a low temperature here and a high temperature here, and define this as positive, then any motion downward, so cooling with time, is gonna have a negative direction. However, if we determine that this is the initial state, and we're just reducing the initial state one direction and this becomes a minus, then this becomes a plus. So you have to be consistent with where you're moving. For instance, just how on a globe you standardize that moving north is north, and if you go 90 degrees to the left, that's west, and if you go 90 degrees right from north, it's east, and then 180 degrees back from north is south. I'll insert this latest part into our makeshift equation. So we went from delta T, and I replaced it with this. I have this minus in front, and now to change it into an actual equation, so we remove this, I'll add a constant in front of my bracket to truly give us the shape of an actual equation, because, well, that way we can determine what the constant for each individual system is. Since it's not a known scientific constant, but rather just a placeholder for other numbers or combination of other constants that are known. It's not italicized. So this is italics, this is not italics, because it's just a placeholder constant. This is just a side note for digital note takers, but with that we finally have a differential equation. Now, as with any differential equation, we separate the variables, so we carry the temperature to the left bottom, and we carry the time to the right, and we get this. Now, here is an observation we can make. Temperature of the room is a constant, so we could do some U substitution. I forgot how much I covered it in the lecture, but basically we find U, so in this case U is the denominator. In this case the room temperature is a constant, so differentiating this as an entire term, so derivative of this, we get this becomes a 1, this becomes a minus 0, and we get this. So differential of U over dt is 1. If the order was reversed, so we have a temperature of the room minus temperature, and we take the derivative of that, well, this is a constant, becomes a 0, and this becomes a minus 1, so the derivative of the other order would be minus 1. However, we already have a minus here, or had a minus there, so that's why I swapped them before. That's the main reason, so we don't have to get a minus 1 and complicate stuff. But yes, the result of the differentiation becomes 1. So if we order it around, so we carry a 1 underneath, we get that dt would equal to du. And now we have a u and a du, so we can simply replace them, or in other words, we have a t minus t room, which is here and here, and we have a dt, which is here, and we just plug these all in the same formula and integrate it. So we essentially get the integral of du over u, which is natural log of u, and then we just substitute u back in, so like this. And it's important to clarify, because we have an undefined integral, indefinite integral, sorry, where did the undefined come into my mind? But yes, we will get a constant. So I will first do the finite integrals to show you what it would look like, because indefinite integrals would be like plus c. So I will add the limits like this. That way we do not have the constant, because we just have these two that cancel the constant. But yes, the integral is between temperature 1 and temperature 2. These are arbitrary temperatures. Let's say temperature 1 is the beginning temperature of the coffee, so the temperature at the start, and temperature 2 is the temperature at some time that we're interested in. The second integral is between time 1, which is an initial condition, so time is 0, and time 2, so the time at which you're conducting the measurement. So as I said, T1 is the initial temperature, and T2 is the corresponding temperature at the given time. And the bottom line of our result, sort of, we can still work with logarithms to get it all into one logarithm. So this is the bottom line I'm referring to. This is the result of this integration. So we integrate this, we get t minus the constant. We can imagine this as the variable t minus constant 2. And then when we're integrating this, we get this. And then we insert the first temperature as the variable, minus the same integral, but inserting the second temperature instead of the variable. And then we get minus kt, because we would have a minus k times 0. So this term is a 0, it cancels out, and we get this. And now, as I said, we can work with logarithms to get it into one logarithm like this. So difference of two logarithms is a logarithm of a fraction. And now we just simply anti-logarithmize. We get this. And now I will carry this part to the right, because we have to account that we should have the t1 value. We have the initial time, we have the time at which we're measuring it. We should have the temperature of the room, and well, we should have either the constant or solve it already from other techniques. So the only variable we're missing is the temperature too. Now we simply carry this initial temperature factor, so the one involving T1, to the right, and then we add the room temperature on both sides, and voila, we get the formula for the temperature at any time. Now, if we broke it down, you already see some sketches here. we would see that the first term states that the room temperature is set as base, so our final temperature cannot be lower than it. Why? We know that the exponent part cannot be negative since the constant itself is positive, and this difference, temperature 1, so initial temperature, is higher than the room temperature, meaning both of these together are positive, and a plus means that temperature 2 will always be strictly higher than temperature of the room. This technically tells us that our coffee will never be as cold or as hot as the room, but it will always be slightly hotter. Now here on the right side, I tried to sketch. Let's say we have a room temperature at the bottom, we have initial temperature at the top, and the temperature at any given time in between here. The exponential part here is a percentage factor. Well, the unit is not percent, it's like a ratio, so like 0.7 or something. And then we know since it's raised to the exponent of negative time, it's essentially e to the power of t under 1. So the higher the time, the lower the overall value. So the higher the time, oh yeah, it is correct. The lower the, like the bam, the over the overall value. So like this. What this means is that we're adding percentages, so from room temperature up. So from the final or initial or whatever up, we're adding the percentages of this delta. So this delta is, the relative value of delta is 1. So we're saying, okay, this refers to 100%. This factor here will tell us how much of this, how many percent of this we're adding on to the room temperature. So, because it's T room plus. If it was T1 minus, we would be subtracting from the temperature 1, and this factor would be slightly different. But this way, we're adding some percentage of this delta, so change between T1 and T room, towards the T room. So T room is increasing for, let's say, if this percentage or non-percentage units would be 0.7, we would be adding 70% of this difference towards room temperature, and our T would be somewhere here. So this would be our temperature. 70% would of course be the value at very low times, because, well, this sticks, so the higher the time, the lower the overall percentage value. In long times, so time near infinity, this would be nearly 0, so almost nothing would be added towards room temperature, if that makes sense. So essentially the orange part is the baseline, blue part is multiplied to purple, so the blue part tells us the percentage of the overall difference between starting and the starting state and outside conditions, and how much that will be increased or decreased from the baseline depends on how we define it. That's why it's important to define the system correctly, or so you understand it. But yeah, anyway, that's defined integrals, so a way to avoid getting the constant or having to solve for one. Now let's do the indefinite integrals. I don't know what's with the defined and undefined with my head today. Yeah, now we're just back here with the indefinite integrals, indefinite, whatever you want to call them. This time the result will not be a difference of logarithms, but some constant on some side, which technically takes the value of the second logarithm, because that's the only difference between the terms. But that's not important right now, because solving this integral gives us this, and a constant on the right. We anti-logarithmize, we're left with this, and we just carry the room temperature to the right. We get our result. Here we see that this is basically the same formula as before, since the latest constant will take the value of the initial conditions, so where temperature is equal to T1 minus room temperature. This is literally hidden in this constant, and that times e to the power of minus kt. Now, when temperature is equal to T1, because time at that point is 0, that's called an initial condition. So if we put that in, so let's say that T becomes T1, and then this is room temperature, plus some constant we're solving for, times e to the power of minus 0, because time is 0, this becomes 1, and then the value of C is literally just T1 minus room temperature. And we can see these two are the same, so whichever path you choose, you're gonna get the same result. So use whichever one is easier for you, Both are correct, just be careful about integral bounds, constants, etc. because they tend to complicate stuff. So yeah, what's the interpretation? As time approaches infinity, the e to the minus kt will approach 0, therefore the overall result will be approaching room temperature, or the addition to the room temperature will be less and less and less. Theoretically, it should never reach it, which it's sort of right because heat is a tricky thing, and we do tend to oversimplify it, but when we get to thermodynamics, I'll try my best to explain it. In chemistry, we'll work with the heat and stuff like that, so we're gonna be assuming that at an infinite scale, we will eventually reach the temperature. But yeah, this is the crash course on heat, and the final formula, technically, both of these are fine. The finite in the finite integrals, these are the same. And this is called Newton's law of cooling. It's a handy little tool. Sure, you need to know boundary or initial conditions to solve for the K constant, or because usually there's certain constants like heat transmission and stuff like that. But other than that, it's not that complicated. It's really, I can't say simple because it does require certain knowledge, but then again, I do give you all that knowledge that you would possibly need, hopefully. So yeah, we didn't cover this much of physics yet for our second example, so this may not be known yet, but acceleration when falling, at least on Earth, well, on average, should be equal to about 9.81 meters per second squared, and it's labeled as g, or gravitational acceleration. It's simplified to say g is equal to 10 for simple physics because, well, the error is minimal because you're already ignoring air resistance. But this is gravitational acceleration. Gravitational constant is something else, so let's save that for another day, please. But yes, this is the acceleration most often used in anything involving falling, potential energy, oscillations, basically stuff that has anything to do with energy balance, most of the time. So when something is falling, one would assume it would fall forever, but that's not true. Something slows them down. If not the impending impact on the ground, it's usually something that prevents them from reaching infinite speed. That thing is air resistance or drag. And basically, the faster an item is moving, the bigger the drag is. Also, there's some other parameters to that. That's why you take parachutes when free falling, because the greater the surface that the air catches in, so on. You get the idea. But yes, so until the effects of both are equal, so the force of acceleration and the force of drag, I'm gonna use it like this because this is slightly more correct. At that point, the speed or velocity of falling becomes a constant. I did write the force of acceleration as I did have to make sure units are the same. Well, that force is called gravity. So we're just gonna say drag and gravity. When these two are equal in opposite directions, just like the system I explained before, if I define gravity as positive because that's the direction we're moving, and drag as negative, when these two are equal, the overall force acting on the body is 0, therefore the acceleration is 0, but we get that eventually. Now, you may or may not know how to calculate the gravitational force or the drag yet. Don't worry, I'll give you the formulas here just so we can use them as to why they are the way they are. We learn that in physics. So, the formula for drag is F, so force of drag, just label these accurately, is minus B times V. Why minus? Because I defined gravitational as the positive force, because we're falling downwards, and drag is slowing us down, so the speed is reducing. This is an oversimplified formula for the drag, by the way. In reality, we would have to use quadratic formula, for a human at least. But let's imagine we're working with a small object that follows this law. As I said, minus basically means that this is a force that works backwards, so if we're moving north, the force would be pulling south. If we move down, it points up, etc. B is the drag coefficient, or dampening constant, or whatever, and basically tells us how many newtons of slowing force the body is experiencing if it's moving at a certain speed. And well, V is that speed. I'm calling it speed because we're working with the linear, so moving in one direction. This is just like a plus minus way. This B constant, coefficient, drag coefficient, whatever you want to call it, it's comprised of some other constants that define it. For quadratic law, there's like pi, 6, density of the air, stuff like that. But that's not important, we're just gonna have one constant here to simplify it. And then we have the mass of an object measured in kilograms, and then we have gravitational acceleration, which is a constant. And these are our two forces which we'll be working today with in this example. Now, we remember derivatives lecture where I wrote acceleration as the derivative of speed with respect to time. So I will bring that back, and here we see that acceleration in this context is replaced by g, so let's correct that in our formula. Great. Now we have our formula for drag and gravity up here. How can they be useful? Well, to get the force of gravity, we need to multiply the g with the mass. So I'm gonna multiply both sides with mass. And this is Newton's second law. Force, yeah, sure. Force equals mass times acceleration. In context of just gravity, we have g. So we replace a with g. So, however, this equation here is true if we ignore air resistance. So this is an ideal system, in a way. But what if we don't? Well, we already have the gravitational effect on the right here, so like this is the gravitational effect. We could subtract the drag or add the negative drag, whichever one you want to understand it, like either you have a force from which you subtract the effect of the other force, where both of these should be positive and the difference makes this one a negative, or you're adding the forces together like we will learn in vectors, which is slightly easier to understand, and then you just say, oh, everything pointing the other direction than this is a minus, and then you just add them together, which makes it easier. Anyway, since I said this the vectorial definition, this is a minus, so we're gonna be adding minus. Kinda hope I make sense. So basically minus the effect of drag, whatever you want to call that. And then after that difference, we will see which effect, positive or negative, will be the primary, or if the difference will be zero and there will be no acceleration. Did I say that correctly? I did. So let's subtract or add the drag to the right, and we get the formula. For the more realistic behavior of a free-falling body, we would have to account for the quadratic, so it's like a lot of constants, 1, 2, 3, blah, 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 times velocity squared. So that would be technically more correct for a human, but this is for a particle, something that's very light, slow moving. But this is slightly more realistic for a free-falling body. What can we tell from it? Based on what we already know, the rate of velocity changes depending on the total force acting on the body. So this is the total force, which I draw later, and this is the change in velocity. So when we get to vectors and forces in physics, we will learn that forces can be added like vectors. So if they point along the same axis, we can write them out like this. And this would tell us that the total force acting on a body would be comprised, in this example, out of three forces. 1 and 2 are pointing in the same direction, while 3 is pointing in the opposite one. So translating that into our example, we get that the total force equals to the gravitational force minus the drag force. And of course, I color-coded them, so it's easier to see what each part represents. So this part here represents the total force. This gives us our first-order linear differential equation, and we know what that means. Time to rearrange into linear form. And we will do that first by dividing all sides with mass and moving the drag force term to the left, because differential of a function and a function must be on the same side. So we divide it by mass and carrying that over to the left, and now we have a matching fit. We have some differential of v plus some term that has v in it, and that equals to some other function. In this case, it's a constant, so because we know integrating factor, I will not do the entire process. For that, you have to check previous lecture 30, because that's where I did it. I will use the final formula that we got, so the formula for the integrating factor, or the result of it. So this was the p of x, which is the function multiplied to the velocity. So we just get integral of time, of that function over time, as the exponent over e. So this is our integrating factor formula, and since b and m are constants and they do not change with time, this integration is like k times dt. Integrating that, we will just draw the integral over dt, and we have k times t. So the result should be b over m times t in the exponent. Now we have our integrating factor, so we will multiply it with each term in our equation. Before that, I write out the product rule formula, but honestly, we don't have to multiply it with every term because only the right side matters, because this is This is representing the right side, this is representing the product rule equal part, whatever that's called. Yeah, so here I will multiply the product with g, and y here is the speed, so this is velocity, mu is mu, this is a horrible scuff, but yeah, let's insert what's what, and we know y is speed, mu is the solved stuff, and r of x is literally just g. So something like this. This is r of x times mu, this is y times mu, and this is basically the product rule, just added it for our problem. Now we just integrate, or sorry, first we rearrange the variables, and we get the integral of this, and left side we just get whatever was in the bracket, because that's literally the integration of d of some function of x, which we're all familiar with. And on the right side, thank God, we have an integral of only one function, because this is a constant. We do not have to do integration by parts. And we do remember we divide the function with whatever is multiplied to t, so we divided with b over m, giving us m times g divided by b times e to whatever was there before, and a plus c. So that's just the integration, because this is like e to the power of a times x. Integral of that gives us e to the power of a times x divided by a. So this is just like the inverted part. Is that it? Yeah, that should be it. Yeah, okay. Now I will divide e to that mass along the entire formula, so this cancels out, and it's under the constant, and we get this. This is the general velocity formula, or equation. Now let's apply initial conditions for a free fall, for funsies. So the speed of falling at time 0 will be 0. So if we insert that into our formula, we get that the velocity at start, or speed at start, is 0. And then there's like a factor plus a constant. So the constant will be minus mg over b. Now let's plug all of that back in, and we can factor that out. And we get our velocity as a function of time. In no way do you need to know the result. It is important that you know how we got to it. But now let's analyze it. When time approaches infinity, so time goes towards infinity, the exponent term will be approaching 0, meaning the right side will then equal to this factor times 1. So this is just like right side equals this factor, because this is like 1 minus 0 is 1, 1 times something is something. So the right side will be m times g over b. And this is also the maximum speed an individual object can achieve, so after the forces balance out, so when force of gravity is equal to the force of drag, the body is no longer going to be accelerating, so that's going to be the highest speed that the body effectively reaches, with no extra propulsion, because if you're pushing it down, it gets faster. However, this is called terminal velocity. And for this very example, it is defined as mass times gravitational acceleration divided by drag coefficient, or the object's weight divided by drag coefficient. As we will learn, weight is actually the force, and it's in newtons. So 9.8 times greater than your mass. But that's a lecture for another day. Eventually, drag balances out with gravity, as I said, and the object will stop accelerating, aka it reaches its terminal velocity. For instance, when you open a parachute, that b is increased a lot, making the maximum speed of your falling much, much lower. That's why people actually survive jumping from heights, because parachutes increase the b, slowing down the fall. I know you will probably expect the phone charging for the third example, but we will cover something like that when we get to electrical circuits. I shall show you an object on a spring going up and down. That's fun, right? Well, it certainly gets interesting, but I'll do my best to show why that is. Now let's look at PhET, where I will showcase what we will be looking at first, so you get an idea of what we're describing. So we are in PhET, and I will open masses and springs thingy in lab. So here I can add a weight on the spring, and I can like swing it. Oh god, let me. So the spring constant is the k, which we will see in a bit, and it effectively like means how thick the spring is. So when I put the weight on it, there's like a certain feel. Let's say like here, I think. Nope, never mind. So this is the stationary position. So equilibrium is the state in which the weight, like the spring is extended normally. So if there's no weight here, it's relaxed. If I add a weight, it should be somewhere here. Now, if I move this weight or mass from the equilibrium position, the spring is gonna stretch and there's going to be force pulling it backwards. So when I release it, it's going to launch up. And then when it launches up, there's like pressure build up here. And when the velocity or speed of the spring moving upwards is not enough to counter the force increasing inside the spring, it's going to launch it backwards. On the left, we can ignore the energy graph for now. There's dampening. If we ignore dampening, it's just going to perpetually moving up and down and up and down. You can play with acceleration and velocity here as well if you want. Or you can add dampening, it's just going to slow down and stop. You can change the gravity, you can trace the graph. Oh, hold on, let me just turn off dampening so I can actually explain this. So we see that this is somehow how this works. And this may already be familiar to you. I'll cut this short and I'll go continue solve the example, and maybe you'll recognize or remember this after we see the formula. So here we have Hooke's law, and this coefficient or constant that was mentioned before appears. This Hooke's law states that the force with which we must act on a spring is equal to some constant times the distance that the spring is moved. Like moved away from the equilibrium state, which I already showed. And we did mention this law before, so it's nothing new. The minus here shows that the force will be directed back into the balance or equilibrium state. So if you pull the spring, the force will act as pulling backwards. So I pull away. I cannot draw? Ah, I can draw, okay. I pull away with force of the hand. The force of the spring will be pulling backward with this formula. So how much we move it away from the equilibrium times some constant, and the minus just tells us the direction. Next, we will write the Newton's law we just learned. The force equals mass times acceleration, F equals m times a. Now, what's the point of differential equations if we don't use differentials for the most basic definitions? As in, acceleration is a differential of speed with respect to time. But what is speed? Well, it's a differential of position with respect to time. So let's plug the latest differential into one for acceleration in here, like this, and we get a double derivative, which we hopefully still remember how to mark, right? So basically, d squared x over d times squared. Now we plug that into Newton's law, so we will basically replace this a with this formula, and we will get this mass. So we can now combine these two equations, but what will that tell us? Well, that will tell us that after displacing the mass at the end of the spring will pull the weight back with some force. And that force will provide acceleration to the mass, which will then be pulled back. And if it's pulled back far enough, spring will have this, well, for now, let's say, energy that will then be converted into a pushing force. More on that on energies and forces when we get to them. Basically, when it gets compressed, it's gonna push back to resist it, ergo giving us another push back. So the spring will go close, and then the force will be concentrated and it will launch it back, and that's how we will get something called oscillation. So the title of this subchapter. And our differential equation will give us the result that describes it. So now that we equal them, let's divide with mass. Basically, we won't really be solving this wholly, like we won't learn how to solve second order differential equations because it's just like normal solving, just slightly longer. I'm gonna go through parallels to logically develop the solution first. So let's rewrite this in an easier to understand way with f of x. So this is the second derivative of some function of x, and this is the function of x, technically. Technically, this is minus k times function of x on the right side, but that's insignificant. However, we see that the second derivative of a certain function gives us the same function, but with an opposite sign. Now, if we think back to derivative tables, which two functions switch between each other, or to be more clear, when taking a derivative of one, we get the other, and then the derivative of that one gives us minus of the original? Yes, that's trigonometric functions, sine and cosine. So these two functions, when we take a second derivative, give us the negative of themselves as the result. As a screenshot from my lecture, from the table of the lecture of derivative rules here, derivative of sine of x is cosine of x, and the derivative of cosine of x is minus sine. So oscillation is the repetitive back and forth variation of a physical measure around a certain central equilibrium point. So equilibrium is like the state in which the weight wouldn't move if you just let it be in it. But if you move it away from that point, it's gonna try to correct itself and it will overcompensate, like a lot of men do. And now that this explanation sounds familiar, it's exactly what these two functions do. So following that, this will give us our general solution to such type of differential equations. So wave functions, sort of. I mean, it's technically a wave. Basically, if you displace it, it's gonna start growing like something like that. You kind of see a sine/cosine function. So from that, our general solution for the function, general formula for a function, is this function of displacement from equilibrium state in regard to time. And it equals to some constant a. This is arbitrary constants a and b that are just like, it's like c or k, they are just there, okay? We determine them through initial boundary conditions. Then that constant is multiplied to sine of omega times t, plus another constant times cosine of omega times t. Omega is angular frequency, and it essentially tells us how many radians of a cycle does the system complete each second. So hopefully I've mentioned it or we remember, we can measure the degrees from the trigonometric lecture. One circle is 360 degrees. However, there is also 2 pi radians. So basically how much it moves each second. We'll get to that in circular motion in physics, so do not get confused about this. It's treated as a constant in this example, okay? So this is just like a k, okay? Doesn't matter for now. So that's all confusing. All you need to know is that it sort of depends, so the omega here, on the mass of an object. So we will have two factors inside each trigonometric functions, where this one is essentially the inverse of mass. So the higher the mass, the higher the omega. Sorry, the higher the mass, the lower the omega, and vice versa. And the other factor is time, which is the important part because, well, it's a function of time. So this is the general oscillation model. Now, to test if it works, we will take the second derivative. We'll take two derivatives of each side. So the second derivative of the left will be x derivative, and the second on the right will basically just be, but that doesn't matter. The important part is that we can factor these two out to get a sort of like this. We get minus some arbitrary constant 1 times function x of time. So the function of displacement through time. And now this is a familiar way to write, right? Because if we edit this like this, we see that this does look exactly like the equation on the left. We have a second derivative of a function of x function, and then we have a minus constant times the normal function that we took the derivative of. And here we also find the formula for our omega. So omega squared is k over m. So singular omega is the square root of k over m, where this constant is just the Hooke's constant. But that's not the point of a lecture, it's just a cool thing to note while on topic. Basically, this is how you would solve such an equation, for instance, because it's waves. Because we understand that this system behaves in waves, so it's going down and up and down and up and down and up. And that way we use sine and cosine, because these functions just fit the description of second derivative. So what does this final equation even mean? Well, a and b are our starting conditions, or are determined by them, and omega is oscillation speed, so how fast the weight or the mass on the spring will be moving up and down, which if we remember from fit at the start of this part, when it went up and down, if we did a side projection of the mass's height, we will probably get a similar curve to sine or cosine one. But yeah, that was it for this mess of a lecture. I hope something stuck. But yeah, I hope the mini test goes well. There was just like general questions, so they see how you analyze the systems to hopefully see if you have enough understanding for basics, which I hope you do. And yeah, thank you so much for tuning in to today's mess, and I'll see you all on our next quest. Bye!